down. Come on. There we go. Well, good morning. The big thing for this next exam, obviously, is proof. That's actually, I got done writing the exam over the weekend, and it's exactly 50% of the exam is proofs. You know, things like element proofs or induction proofs or different things. The biggest problem we have with proofs, and everyone has the same problem, is how do I start and how do I finish? And I'm going to make it really simple. I want to prove A implies B. Doesn't matter what A and B are. They're statements. A could be a formula, it could just be some sort of simple statement. So we did proofs earlier on. For example, we're going to do something about an odd integer. And I want to prove properties of odd integers. Maybe something like the square of an odd integer is still an odd integer, right? That's something we've done. We've done things like that nature. So I would say something like this. I want to prove the square of an odd integer is odd. So I'd say there exists t and z such that n equals 2t plus 1, and then I move on. Everything I said is false. Not one thing I said was true. Why? There exists no t and z such this is true unless what? Unless n is odd. But if I didn't assume n is odd, then n absolutely is not odd. In fact, there's not even a possibility. It's a probability of 0 that n is odd unless I assume n is odd. Are all numbers automatically odd because that's what you need them to be? No, the first step of my problem would be what? Assume or suppose n is an odd integer. Does everybody understand? If n is not an odd integer, then nothing that I say is true, no conclusion I get will be valid because I have no assumption. Therefore, there is nothing true. The assumption is the law. It is absolute, it's irrefutable, it is the evidence in the trial. It's the only thing that can't be questioned. But you have to clearly state what the assumption is, and a lot of times we're doing proofs without ever. I got many good proofs without ever mentioning what the assumption is, which means that nothing we're saying is true because we're being very specific. The assumption leads us down a very narrow path of things that can possibly be true, and those things are not true in general of the assumption. So when we're doing, let's say, an induction proof, let's say we're doing a summation problem. Let's say we did one already. I want to prove this one, okay? That's awesome. So we proved it for 1, and then we assume it's true for k. But at some point I have to say, assume or suppose I don't care what word you use. It's really it's a semantics thing. What makes more sense? Kind of like, when do I use and when do I use but? We know they mean the same thing, but if you were saying something, oh, I went to the store today, but I forgot to get the milk. You don't say, I went to the store today and I forgot to get the milk. That's the same statement, but it just doesn't feel right, does it? So assume or suppose, I'd say, assume this is true. This is now absolute. Can't be questioned, and now I'm going to do my proof. But a lot of times, we're not doing that. Or on the divisibility ones, we're saying, suppose this is divisible, and then when we're getting to the proof part, we are proving the divisibility part. No, the assumption. So let's do one of these. I've got like, I don't know, let's say it was 3n minus 1, I want to show is divisible. Oops, sorry. This is kind of easy. So then, okay, now let me start with 3k plus 1 minus 1, and let me start going. This is true, but you haven't said anything yet. You said, yes, it's divisible by 2, but what does that actually mean to be divisible by 2? That means there exists a t and z such that 3n minus 1 equals 2t. This is my assumption. This is not my assumption. These are just words. My assumption has to be a mathematical statement, because isn't this the thing you're now going to use to prove the next thing? Yeah, so on a problem like this, almost everybody in the class completely left out this. They said this, and then they started doing math and introduced this sort of halfway through the proof. It's like, no, you're not proving this statement. This can't be part of the proof. This is the assumption. This is what's going to allow me to prove the next thing. Now, the last thing is, most of you guys are writing proofs that are fun. But you're writing stuff, how do I know when I'm done? So what am I assuming here? I'm assuming A is the truth. I'm going to go dot, 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 therefore B. Whatever B is. My last statement should be, therefore B is the truth. I'm starting with A as the law, and I'm showing at least a B is the truth. I'm not going to have you prove things that aren't true. We've already done that with counterexamples and contradictions and things like that. And you guys did a really good job. Now I just want to do a straight up, maybe it's an element proof, maybe it's an induction proof. But at some point I need to state what is it that I concluded. And hopefully it's pretty much exactly the same. So I want to prove that this is divisible by 2. So somewhere along the line, shouldn't your last statement be something like, this is divisible by 2? Either in words or in... What does this say in words?
2 divides 3n minus 1.
So 3n minus 1 is divisible by 2. This or in words. But a lot of times we're finishing the proof and we never actually said this. We're stopping a step or two short, and what we said was true and would lead to that conclusion. But if that's what I'm trying to prove, then it should be the last thing I say. If someone was reading your stuff, would they say, I don't think they're finished yet? Now, we've done a few problems in class, and I kind of trick you, and I'll say, now what? You've heard me say that a few times, right? I'll go, now what? And go, oh, we're done. Oh, we are done. And the reason I'm asking you now what is do you recognize that we're actually finished with the problem at that point? Because sometimes we want to keep going because it's so much fun, right? We've talked about that one before. Okay, so I want to do a little bit of the weekend stuff. I always like to start with the weekend stuff a little bit, just in case there was a little bit of confusion. Now, in remedial algebra, and when I say remedial, I mean as far back as pre-algebra, we introduce language, we introduce concepts that we know are not going to stick right away. When do you learn the 11 properties of real numbers? Right? Commutativity, associativity, identity, inverse closure, for addition, for multiplication, and there's distributive property. We know these inside and out. We use these all the time. We use these as justifications. When do you really learn these and hammer these in? Pre-algebra or even sooner. It's in the beginning of every pre-algebra course. So that's the first time you're exposed to them. Do you think a pre-algebra student really understands them deeply? And they can get right answers, but when they're solving a problem, sometimes they're not really sure. But there are other concepts we introduce really, really early on in mathematics, whether it's high school geometry or pre-algebra. We introduce the language and we introduce the concepts, and it's not till way later that we really understand them. So we are talking now, this is the big weekend and today, equivalence relations. Now, an equivalence relation is, think of it as any sort of comparison. It could be simply as this. My comparison is the following. Is taller than. So Biff is taller than Joey. That's my comparison. It's either true or it's not true. There's no calculation. So is parallel to. I could be talking about lines or planes. I could say, well, in that matter, is perpendicular to. I could be talking about shapes, and I could say my relation is congruent to. I could be talking about numerical values, and it could be greater than, it could be less than, it could be equal to. Any form of comparison that you could possibly use would form, or potentially form, I'd say, an equivalence relation. Now, an equivalence relation means there are 3 parts that all must be true. Does anybody remember the vocab? Because it was over the weekend. One starts with an R, one starts with an S, one starts with a T.
Reflexivity.
Reflexive? Just reflexive.
Reflexive. Symmetric.
Symmetric.
Transitive.
And transitive, yes. Transitive is by far the most used and most important because it's the one that we use anytime we justify it, like a substitution in an algebra or calculus problem. These are the 3 pieces that form an equivalence relation. Now, I can have a comparison, a relation. That's what you were doing over the weekend, relation. I can have a relation be symmetric. I can have a relation not be transitive. I can have a relation be transitive but not reflexive. If a relation is all 3, then it's called an equivalence relation. And the easiest ones that you can possibly think of, the most important ones, one of them looks like this, the other looks like this. In other words, the equal sign is an equivalence relation. and the congruence. Think of this as geometry, right? Shapes being congruent. Those are the easiest and most powerful. Now, I have a set S. I just have set S. And A and B are elements of set S, and I'm going to keep that as vague as possible. A and B could be shapes, they could be people, they could be numbers, they could be variables. They're just two things in set S. Set S might be my class roster. Okay? Now, I have a relation, let's call the relation T. T could be the equal sign. It could be a greater than sign. It could be a parallel sign. It could be is taller than, is prettier than, is poorer than. Any way you can compare two things that are the same types of things. I can't say this line is poorer than this number. That doesn't make sense. But I can compare a line to another line with things like parallel or perpendicular, right? We know all sorts of ways. So I have two things in S. I have a relation T. We say that A, T, B, this means they are related through whatever my comparison is. Now, my comparison, we're going to do things that are purely algebraic, just to make our life easier. But this just means they have a relation. So my relation could be is taller than. All right? So it could be, you know, A is Jordan and B is R. Then is this a correct relation? Jordan is taller than R. You'd say yes, so they're related. Now, if that were true, would this be true then?
No.
No. So reflexive is if A, T, A. Symmetric is A, T, B, if and only if B, T, A. Now, I'm going to use an easy one. Shapes. Congruence of shapes. I have two triangles. My first triangle is congruent to my second triangle. I have two triangles that are identical. So is the second triangle also congruent to the first triangle?
Yeah.
If I have two identical, yeah, you say that's kind of a no-brainer. But the is taller than relation, if A is taller than B, then B cannot be taller than A. Do you agree with that? Now, reflexive seems like it would be an easy one, but can you be taller than you? No. You can't be taller than yourself. A number can't be bigger than itself. Ooh, so reflexive is not automatic, is it? Right? Reflexive is not automatic, but can something be to itself? Is a shape congruent to itself? Yes. Is a number equal to itself? What if I said, instead of is taller than, how about if I said is at least as tall as? What would that mean? At least is greater than or equal. Oh, so can you be at least as tall as yourself? Yes. You cannot be taller than yourself, but you could be at least as tall as yourself. So greater than or equal would be a reflexive, or would satisfy reflexive. Symmetric is not tricky, but it means it's got to go both, my comparison has to go both ways. Oh, okay, so that's a little bit trickier. If A is greater than or equal to A, is A also less than or equal to A? No, can't be both. So that one won't work, but at least, you know, now transitive is if A, B, and B is to C, I need to throw another one in there, okay? Let me throw a C in there. Then A is to C. Now, most of us are familiar with transitive because we use that in algebra all the time. You're doing an algebra problem. Let's say something as simple as you have two equations, okay? Think baby algebra. I want you to solve the following. 3x minus 4y is 8, and y equals 2x plus 1. I want you to solve this. There is exactly 6 ways algebraically to solve it. I can graph it, which is not a great idea because I might not be able to easily read the intersection. I can use substitution. I can line them up and use the addition method. I can use a matrix. I can use Cramer's rule, right? Determinants. I can use the inverse of a matrix. That's kind of overkill, isn't it? I have 2 equations, 2 variables. I think most of us would agree, you know what? Let me take this y and let me stick it in here. That would be the most logical way, the fastest way. What allows me to do that? That's the transitive property. If A is to B and B is to C, then A is to C. That's what we do when we do substitution. Oh, Okay, so whenever I have something fairly complicated and I want to substitute something in there, I'm saying the new thing is still equal. The substitution property in algebra, which is probably what most of us would have done here, that's an example of using transitivity. Okay, I can't do a substitution unless something's transitive. Can you do substitutions on inequalities? There are certain things you can do. If Samuel is taller than me and we both grow 3 inches this summer, is he still going to be taller than me at the end of the summer? Yeah. There are properties that we can do. If let's say Benito makes more money than me and we both get our salaries doubled this summer, will he still make more money than me? Yeah, so I've just introduced the addition and multiplication properties of inequality. But can I just arbitrarily do other things to inequalities? Can I square both sides kind of thing? Can I take... No, because now we have the problem with negatives. And with equalities, there's things I can do. With inequalities, not so much. So, but the transitive property holds more often than most things. I am thinking of 3 lines on the plane. 3 distinct lines on the plane. And I'm telling you that line A and line B are parallel. Now I have a 3rd line on the plane, let's call it line C, and I'm telling you that B and C are parallel. Okay, I want this to be an oh duh. Can you make a conclusion? Do we all agree with that statement mathematically? Yeah, so on the plane, parallel would satisfy transitive. And by the way, if A is parallel to B, would B be parallel to A?
Yes.
It's like, duh. So parallel satisfies both of these. So obviously it satisfies all 3, right? I'm looking with my left eye so you know something's up. Can line A be parallel to line A?
No.
Why not?
So it's self-intersecting.
Because it intersects. In other words, we'd say it's concurrent. Why is that bad? Because parallel can't intersect. Oh, and line A intersects line A infinitely many times. Ooh. Imagine that. Parallel on the plane satisfies these 2, but not this. So is parallel an equivalence relation?
No.
No. Now, how about if I'm in 3 dimensions? Turns out parallel wouldn't matter. But how about perpendicular? Let's go back to 2 dimensions, because I want this stuff to make sense. Okay, I have line A, I have line B, I have line C. And here's what I'm telling you. I like using geometry when we're doing this because it's really easy to conceptualize. I'm telling you that A is perpendicular to B. I'm telling you this. You don't have to prove this. And I'm telling you that B is perpendicular to C. That's all I'm telling you. Look at these 3 things. Are any of them true? We're talking on the plane, not in 3D. 3D is different rules for things like parallel and perpendicular. It gets very confusing. Let's keep it to the plane. Is the perpendicular relationship reflexive?
No.
Why not?
Because it's the same line.
Yeah, A can't be perpendicular to itself. So do we all agree that the perpendicular relation is not reflexive? How about symmetric? If A is perpendicular to B, can I say that's if and only if B is perpendicular to A?
Yes.
Are you guys cool with that one?
Yes.
Yeah. By the way, that would be true in 3D also. Now the 3rd one. A is perpendicular to B and B is perpendicular to C, so obviously A is perpendicular to C, right? Right? Wait a minute. Would that be correct to write it like that? In fact, in 2 dimensions, tell me about A and C.
No parallel.
They would have to be parallel. Ooh, so perpendicular badly fails this. Now, this is an interesting one. Now let's go to 3D. Oh,
Are those at the bottom of transitive, are they supposed to be T's?
oh, because my relation was, what did I say? Oh, thank you. Oh, good catch there, Benito. Somebody's gonna look at this later and go, what? We changed notation and the problem. Yes, those are all supposed to be T's. Now think 3D for a moment. I have that plane. I have that plane. I have that plane. That's plane A, that's plane B, that's plane C. A is perpendicular to B. B is perpendicular to C. Is A perpendicular to C in this case?
Yes.
Yeah, in this case, so can I set up a case where perpendicular is transitive? Yeah, if I was talking about, let's keep it simple. I'm talking about a rectangular prism. That's what this classroom would be technically. Forget the little inlet here. Okay, y'all cool with that? This room's a rectangular prism. So if I'm talking about the sides or the faces of a rectangular prism, does transitivity hold? Actually, it does. So perpendicular can only be transitive if I'm in 3D, by the way. It's absolutely not going to work in 2D. So I do have to know the conditions. But these three things individually should always be really simple for us to understand. But this is stuff you may never have done in your life. And the funny thing is, we introduced this in remedial algebra. How many times in calculus did you use any of these? How many times in linear algebra did you use these? You didn't, did you? Did you use it in trig? No, you might have in your geometry class, depending on your geometry teacher, but that's probably not last semester that you guys were in high school geometry. Most of you were not, maybe even last fall, no? So here's the problem. We introduced these in baby algebra, and when do we talk about them? This class, really? So does anybody remember the details? Of course not. But they're all pretty simple concepts. If I leave it really general, yeah, okay. If first thing is to second thing, then second thing is to first thing. That makes perfect sense. So now let's do a very specific problem from beginning to end so you can see what it looks like. Because this should never be hard from an algebra standpoint, but like everything else in this class, it's a conceptual thing. Those of you who have had linear algebra, the algebra in linear algebra is not very hard, is it? It's baby algebra. But like a lot of other things, it's you got an answer. It's not the answer, it's what the heck did I just say? What does this actually mean that I've answered the question and I have numbers, I have some sort of concept, but I don't know what I just said. Well, that's what this is. What did you just say? So let me do one. Okay, I'm gonna go real slow and I'll put it right here, all right? I'll use T. And the author loves using R for relation. I don't like using R for relation because the author's also using R for the set of real numbers. And if you look most of the time, there's really not a distinction on the way they're making the symbol. They're saying call R a relation, and then later let X and Y be elements of R, and then you're looking going, wait a minute, are those real numbers or are those the relation R? And in some cases, they're supposed to be real numbers. But there's not a real clear distinction, so I don't like using the R. Just because it'd be correlate, kind of like I'm saying, let me call my relation capital Z. That's probably a bad idea. We're using capital Z for integers, right? So we're not using capital T for anything. So I'm going to say let T be a relation on the set of integers, okay? And I'll explain what this means in a moment, of congruence modulo 6. Now, if you actually did the reading in the previous section, modulo 6 means my denominators are 6s. That's all it means. It means I'm taking something and I'm dividing them by 6, okay? Because there can be remember, there can be a remainder, that kind of thing. And so here's how I'm going to define my relation. For all A, B, and C in Z, I have to throw the C because we're going to need it for the transitive later. Okay, for all A, B, C, and Z, we say that A, T, B, if and only if 6 divides the difference of A and B. So no matter what A and B are, their difference has to be a multiple of 6. Does that make sense? Because A minus B needs to be divisible by 6, which is basically the same as saying A minus B needs to be a multiple of 6. That's how I'm defining my relation. So does this relation apply to all real numbers? Question. True or false? Based on this definition, is this true or false?
No, this is true.
Is 2 minus 8 divisible by 6? Yes, so this would be true. Yeah, by the way, don't put an equal sign. This is a statement. This doesn't equal anything. It's a true or false statement. True or false?
False.
False. I want this to be easy. Does that make sense? Oh, okay. So I'm not looking at specific numbers, only certain numbers apply. No, you're always looking at pairs of numbers. Oh, any two numbers that I put together, as long as they're divisible by, the difference is divisible by 6. This is how I'm defining my equivalence relation. Or excuse me, this is how I'm defining my relation. I'd like to determine if this is an equivalence relation, which means I'd like to determine if all three of these are true. Now, on your quiz for this, I gave you something similar, and I didn't ask if it was an equivalence relation. I just asked you to determine if it was reflexive, symmetric, and transitive. Because in sections 8.1 and 8.2, we haven't defined equivalence relation. All I'm doing now is saying if all three are true, then we call that an equivalence relation. There's an infinite number of relations. There's an infinite number of ways you can compare two things. They don't even have to be numbers, right? They could be lines. They could be people. There's an infinite number of ways I can compare things. And I can test reflexive, symmetric, and transitive on every form of comparison that exists. But those comparisons that satisfy all three, those are called equivalence relations. Does that make sense? The relation is simply the way you are comparing. This is the way I'm comparing. I'm taking a difference and I'm asking if it's divisible by 6. That's how I'm comparing the numbers. So, I'll walk you through it. So the first one, I'm testing for reflexive. It is or it is not reflexive. So, true or false?
True.
How do you show it?
Because it will be 0 and 0 is divisible by 6.
0 and 6. This is actually right here. Or, by the way, you could, probably a cleaner way would be to do it like this. That might be an easier way of saying that. A common mistake that I've seen recently is the 0 freaks us all out, doesn't it? We're not sure what to do with it. 0 can be the numerator in any quotient. That means that every integer divides 0. We know that. But 0 can't be the denominator in any quotient. So no number, 0 does not divide any number. There's a common confusion, and this happened in the recent quiz. A lot of us are confusing these. Right? You can't have the 0 on this side. Because that would, remember, the number on the left is the denominator, and you're saying that quotient is an integer. If 0 is in the denominator, you don't have an integer, you have undefined. So I can have 0 in the numerator. All integers divide 0. Okay? So I'll put, okay, that's true. Check, however you want to say it. We've proved reflexive. Because every number, when I subtract itself, that result will be a multiple of 6. We good up? Now, that was the easy one. Symmetric. So I have to assume something. So I'm going to say for all A and B, if 6 divides A minus B, then tell me what can I infer? Then what? There exists a t in the set of integers such that
A minus B equals 16.
good, such that A minus B equals 16. That's what that statement means. I'm saying, if this is true, then this is true. Then what? Tell me about B minus A. If A minus B equals 16, then what's B minus A? Negative 16. Yeah. We're overthinking. Ooh, that's not what I need. That's negative 6. Is that a multiple of 6? Yeah. Here's the step that, believe it or not, escapes some people. What if I wrote that as 6 times negative t? Is that a legal move? I don't need it to be negative 6. No. I need it to be positive 6 times something. Okay? Negative t is an element of z since, oops, integer multiplication is closed. I need that to be a multiple, excuse me, I need this to be a multiple of 6, so I need this to be an integer. So what have we just proved? I like using words like thus 6 divides b minus a. Did we just prove 6 divides b minus a? Yes, because we showed b minus a was a multiple of 6. Did that require incredible cleverness there? Or is that more of an oh duh? Yeah, it's probably closer to an oh duh. Yeah, by the way, if I had said, oh, the result needs to be positive, then obviously reversing the order of subtraction would have messed it up. But I don't need the result to be positive, I just need it to be a multiple of 6. And by the way, for all possible integer values, isn't the result going to be negative exactly half the time? Right, because I can subtract in either order. Now, transitive, this one's going to be a little bit trickier. By the way, do you think it's going to be true?
Should be.
It seems reasonable. Transitive. Okay? If A, T, B, and B, T, C, so this is what I'm assuming. So basically, if these statements are true, what should my conclusion be if I did it right?
ATC.
ATC. That's what I'm hoping for, okay? So actually, you know what? I probably should write this. BTA. I really need to say that, because that's the form. I mean, that's what we're showing, but that's probably, I don't care if you stop here. You're saying it very cleanly. So I need to show that A minus C is a multiple of 6. Okay? Well, what can I assume? If that's true, there exists an R and an S in Z such that, what? 6, well, remember this means 6 divides A minus B. So how about if I said A minus B is 6 R and B minus C is 6S. Is everybody okay with that? Because again, I'm saying A is related to B, that means their difference must be a multiple of 6. I got it right here. Okay? How can I get A minus C though? I need A minus C.
Add A minus B and B minus C.
Now, in general, this is not something you have to prove. If A equals B, then A plus K equals B plus K. Is that true or false? Is that always true? Yeah, this is not transitivity. This is called the addition property of equality. Whenever you have an equality, if you have the same property to both sides, you preserve the equality. That is not something you have to prove. That is an axiom. That's an absolute, we know that's true. Oh, okay. That's what I'm going to do. I'm going to add the same thing to both sides. I'm going to add, so if it helps, think of it like this. Add. That's exactly what I'm going to do. Okay? Then how about A minus B plus B minus C should therefore be 6R plus 6S. Everybody okay with that? Well, what do I have on the left side?
A minus C.
On the left side I have A minus C. On the right side I have 6 times R plus S. Let T equal R plus S. T is an integer since int addition, I'm running out of room, is closed.
Are you sure you want to use lowercase t?
Did I already use?
In symmetric, I guess, but does it map?
Oh, it does. This is a whole new problem.
Very
Yeah,
different.
good question. I'm not double dipping. Think of this as an entire proof contained within itself.
Oh, okay.
I can reuse the R's, the S's, and the T's, because now this is a whole new proof that has nothing to do with the previous one. I'm not taking any of those results and carrying them through. That's a good question to ask. Can I reuse, guys? Yeah, because I'm starting over. That'd be kind of like saying, now on problem 2, you can't use R, S, or T. What if I'm doing 20 problems? I've run out of letters in the alphabet. No. Within the same problem, you shouldn't be using the same variable. But this is a completely different problem than that in a sense. And I typically like to use the letters I'm not using as I'm using A, B, and C, keep these. Now, what have we got? What have we just shown? A minus C equals 6T, so 6 divides A minus C and therefore A, T, C. Have I proved transitivity? Either this statement or this statement, but at some point, everything I've said here is true. But am I done? I can't conclude transitivity yet, because transitivity means I've proved that 6 divides A minus C. So I have to actually state it. So 6 divides A minus C, or A is related to C, because that's my definition of my relation. Either one of these, have I now got transitivity? Yes. So going back to the original problem, is this relation T defined this way? Is this an equivalence relation? Yes or no? Yes, because it satisfies all three. If one of them failed, and that is possible, if one of them failed, then it's not an equivalence relation, but it could still be symmetric or transitive. So it's good practice to try to show all of them. If the question is, determine if it's reflexive, symmetric, or transitive, that's the question. Well, you gotta do all three. If I said determine if it's an equivalence relation and it fails any of them, are you done right the moment it fails? Yeah, essentially you are. Okay? Everybody okay with this? It's not complicated, but we have a goal. Now, when I define an equivalence relation, I automatically partition my original set. Now, my original set can be anything. It can be people, it can be shapes, it could be lines. In this case, we're using integers. Did I specify whether my integers had to be positive or negative? No, it didn't matter. It didn't matter. They just had to be integers. And I needed integers because if I use real numbers, then I can find examples all over the place, right, that won't work too well. Now, I want to break this down into what's called a partition. And so within my equivalence relation, I have to have the equivalence relation. That has to be established first. A lot of times you're going to be told, using the following equivalence relation, okay, I don't have to prove it, I'm being told it is. I want to partition this into the appropriate, what are called equivalence classes. Now, in the last example, I'm going to use this particular one, right? The modulo 6. We all agree, let me do a simple one. If I said 18T6, that one's fine. But what if I said 18T5? You'd say that's not fine. Why?
The result isn't divisible by 6.
So describe the result. Well, I could say 6 divides 18 minus 6 because 18 minus 6 over 6 equals 2. Okay, how about here? 6 does not divide 18 minus 5 because 18 minus 5 over 6 is what? 2. How about if I said mod 1? Everybody okay with that statement? Did I do that right? 18 minus 5 is 13, 13 over 6. 6 goes into 13 2 times with 1 remainder. So it'd be a mod 1. But you know what's funny is, what if I did 19 and, let's do another one. What if I did 19 and 6? Two different numbers. You say, no, that's not going to work either. Why? Because 19 minus 6 over 6 is 3 mod 1. Huh. Both of these had a mod of 1. I wonder if somehow I can put other things together. It turns out, if I count by 6s, think of it this way. If I count by 6s, they're always going to be in the equivalence class, agreed? But what if I count by 6s? No, but I don't count by 6s. What if I have some other number involved and say, well, no, that's not going to work? How many different mods could I have if I'm looking at two integers? And my denominator is always a 6. How many mods are there? Trick question.
5.
6. Because I can have a remainder of
0.
0. So I'm going to get exactly 6 equivalence classes here. And I'm going to show you how they're related. This is not tricky, this is a definition. There's no, the algebra involved here is pretty low level, okay? So, I want to do this very specific one, okay? So again, going back to the original statement, A, T, B, if and only if 6 divides A minus B. Now let's go to that statement. I'm going to start with the number A, not the number B. I'm going to start with the number. A can be any integer you want it to be. A is 5. Well then if I count by 6s, right, then I'm always good, aren't I? But if I didn't count by 6s, I might not be good. So we're going to call the first equivalence class, and we use rectangular brackets. This is an equivalence class. There are an infinite number of numbers here. I just need to name one of them. For example, if A was the number 1, and I said, now I want you to count by 6s, could you tell me all the numbers in this set? Yeah, count by 6s in both directions, the set is infinite. But you gotta have one number. You have to know one number. If I gave you a recursion and I asked you for all the numbers, you couldn't tell me unless I gave you a first number. Agreed? Oh, once I gave you the first number, now you can tell me. Sometimes I need to give you 2 numbers. So we're going to define this as the set of all x's in Z. I need to state that. Remember, if I just said the set of all x's, are they automatically in the integers? If I don't say anything, where do those x's live?
Real number.
In the real numbers, and that's not what I want. I only want integers. So I actually have to specify x as an integer. Okay, this is when we have to say it, okay? It's all of these such that x, t, a. Well, what does that mean? That's the same as saying the set of all x's in the integers such that, I'm going to erase this. I'm going to rewrite the set multiple times until I get to a form that's useful, okay? Such that 6 divides, and this is a big vertical. Sorry. This is awful. I'm using vertical twice in here. 6 divides A minus B. Well, that's equal to the set of all integers such that, what? Such that x minus A equals 6t. Is that true? I want to keep restating it in a more useful form. So this is my original equivalence classes. The set of all, the equivalence class for A is the set of all numbers such that that number and A are minus, or x minus A is divisible by 6, which is the same as saying x minus A is 6t. And that's the same as saying the set of all x's in Z such that x itself is equal to 3t plus A. I'm sorry, 3t, sorry, 6t. For t in the set of integers. Huh. Now remember, I call this the equivalence class of the A. What would the equivalence class then of 0 be? Now, I want all of the numbers that are in the same class, so that means that that's my A, if you will. What does this set of numbers actually look like? Well, first of all, what is it? It's the set of all things such that x equals 6t, well, if you want, plus 0. I know it's redundant, but we'll throw it in there. So what would this be? If I wrote it in words, it'd be the set of this is actually how we write it. It's kind of cool. Have you ever seen this? The dot, dot, dot at both ends? Because that means it's going that way forever, and it's going that way forever. Is that pretty easy to read now? I'm starting at 0 and I'm counting by 6s forever in both directions. That would be called the equivalence class of the number 0. So pick another number in that class, just for that. How about 12? Again, the same original problem. I'm doing the whole, 6 in the denominator thing. I'm not changing that. That's throughout this problem I'm doing that. If I said start with 0 and count by 6s in both directions forever. Start with 12 and count by sixes in both directions forever. What do you think? Are they the same?
Yes.
Yes. So we use, in this case, 3 bar, and this is really odd notation. This 3 bar, we actually use the words congruent, which seems like an odd choice of the word congruent, but we don't use the typical congruent symbol. Now, we used this earlier for equivalence, didn't we? But in this case, that's what it means. The set that starts at 0 and counts by sixes in both directions forever is the exact same set. So those sets are identical in every conceivable way. I don't put an equal sign because this isn't a numerical quantity, but this set is the same as this set, but it's a very particular congruence class, it's called. So the congruence class of 0 is the same as the congruence class for 12. Could I come up with other ones that are the same? Yeah, how about 6 and 36 and negative 12? Do you all agree that would keep being the same over and over and over again? Well, that's cool, but I said a moment ago, aren't there 6 different possible remainders, 6 different mods? So what if I want, just for the heck of it, what if I wanted this one? Oops, it's supposed to be black. They only switch tops on me. I want this. Well, this is equal to the set of x's in z such that x equals what? 6t plus 1 for t in z. So what would this class look like? I just added 1 to every one of these elements. So far, so good? So if I said, well, think of this, can you give me another one that's congruent to this?
7.
7. In fact, if I count by sixes forever, won't I get every number that the difference will be a multiple of 6? That's why I'm going to have 6 different equivalence classes. Oh, tell me a couple more that I might be able to get. You think I'm going to get 2 maybe, and 3, and 4, and 5, and of course 6, right? Right? No, why not?
Because that's resetting
That's the same
again.
as 0.
Oh! So how many? 1, 2, 3, 4, 5, 6. How many representations of this class are there? Infinitely many. It doesn't matter which one I use. The most logical one is to use these ones because those would be the actual remainders. Do you agree? But 0, 6, 12, all of those are the same class. 1, 7, 13, they're all the same class. Typically, it's wiser. It's wiser to use just the smallest number you can use. It just makes it easier to keep track. So I started with this relation. We proved it was an equivalence relation. We proved symmetric, transitive, reflexive. We proved that. Now I'm saying, since it's an equivalence relation, can you tell me the individual equivalence classes? Piece of cake. That part should be easy. Okay? Everybody okay with that? There's just nothing about that, hopefully, that troubles us. So now, what if I asked you the following? These are mathematical statements. Remember, there are an infinite number of numbers. Once I use the rectangular brackets, it means there's infinitely many numbers. Is this equivalence class equivalent to this if I'm doing mod 5? Is this equivalence class equivalent to this if I'm doing mod 4? I want this to be easy, but you have to know where to look. In the previous example, we were using mod 6. So in simple English, that means I'm counting by 6s in order to keep the difference a multiple of 6. So if I'm mod 5 means I need the difference to be a multiple of 5. Would you say this is true or false?
True.
True. How about the second one?
False.
Why?
Because the mod would be 1 if you were counting by, if you were counting by fours.
Well, because 3, if I counted by 4s, wouldn't get me to 13, would it? Well, counting backwards by 4s wouldn't get me to 3. That's probably the easiest way to think about it. Or 13 minus 3 divided by 4 isn't an integer. Is that the same statement? Does it matter how you look at it? No. Your conclusion, you said if I count by 5s, I get to here. An easier way is take the difference, is the difference divisible by 5? Is the difference divisible by 4? That's really the easier way to look at the question. So, does everyone see how we got the answer? There's not a lot of work to do, so let's do a few of these. This is a question I love to ask. So I'm not asking you to even create the equivalence classes. By me telling you what the mod was, I'm already telling you what the equivalence class is. Okay? How about if I do, let me see. I'm going to do it with numbers this time. Okay? What if I set it like this? I want 12, technically think of this as the equivalence class that has all 12s in them. Is this congruent, or is this the same equivalence class as 8? Mod 2 is 12 the same as 8. Mod 3, 12 the same as 8. Mod 4, and 12 the same as 8. Mod 5. All right. Are any of these true? It might be the easier way. Are any of these true? Because it's a true or false statement.
Are all of these equivalence classes?
Yeah, I'm saying now different notations sometimes will drop the rectangular brackets because of this, the way the problem's stated. I'm showing you that because when you're looking in the textbook, you're going to see both. This is what tells you. I'm saying, oh, is the number 12 equivalent to the number 8 mod this? That's the same as, am I going to get remainders or not, kind of thing. So imagine, mentally put the brackets in a sense. I'm just showing this is an alternate form of notation that you will also see. So, are any of them true?
First and third ones.
You say this one and this one, because the difference is a multiple of 2, the difference is a multiple of 4, but the difference is not a multiple of 3 or 5. That is absolutely correct. That wasn't bad, was it? Oh, okay, that's kind of easy. All right, let's do. First one's confusing you. Mod 1 means what?
All the set of integers.
Well, but what does the mod 1 mean?
Divided by 1.
It means dividing by 1.
Yeah.
Oh, that's basically always going to be true then, isn't it? Is that a trick question? It's a tricky question. That one's always going to be true. The mod 1 means that's going to be, right? Mod 1 is going to be, I'm dividing by 1. It's like, yeah, that's going to always work. How about the second one?
Yeah.
Yes.
How about the third one?
Yes.
I'm seeing both ways.
Wait.
Well, the difference is 0.
Oh, yeah,
The
yes.
difference
Yeah,
is
yeah.
0,
That's true.
so it's true.
If the difference is 0, it's always going to be true. Yeah. By the way, you're not going to have, this number here is not going to be negative generally because we're talking about The differences can be positive or negative, but we're always gonna use a positive number for the mod part, okay? How about, starting to run together here, I know. True or false?
False.
So, are either one of them true? I'm hearing more than,
The second one's true.
you like the second one? Because the difference of 16 and 0 is divisible by 4. Another way of thinking about it, again, this is if you were showing this to little kids, you don't use words like the difference and the quotient, but you'd say, if I count by 4s, count by 4s forward or backward, doesn't matter which way I do it. Can I get from one to the other if I count by 4s? Can I get from one to the other if I count by 4s? No. So that's why this is a false and this is a true. If you were explaining to a child, that's probably the words you use, and sometimes it's easier if we think of it that way. Counting by 4s means that the difference is divisible by 4. Okay, this difference is not divisible by 4. So we all good with that? So, big picture now. I have to understand the meaning of reflexive, symmetric, and transitive. That's critical that I understand that. Proving them for the isolated situation or proving that it fails shouldn't be that terribly hard, okay? Can we come up with a situation? Let's do numbers. So let's say I'm going to define a new equivalence relation. So I used T already. Let me use I'll use T. Be the relation how about on Z such that for all A and B and C, I really have to do the C for later. In Z, A is related to B. How about if A, B is odd? I like this one. Okay, I just made this up. So A and B have to be integers. Because otherwise, by the way, odd and even have no meaning if you're not talking about integers. For example, if I was talking about imaginary numbers or complex numbers in general, there's no odd or even. There's no positive or negative either if you're talking about something else. So the terms positive and negative have to be real numbers to begin with, but odd and evens very specifically have to be integers. On one of the proofs recently, we were doing a proof by contradiction, I think it was, and someone's conclusion was, it's contradiction because the value I got can't simultaneously be an integer and a rational number. That was actually the conclusion. What do you think about that statement? So they can't be an integer and a rational number simultaneously. All integers are rational numbers, so that's kind of false infinitely many times, isn't it? Yeah. The intent was something else, but to say something can't be an integer and a rational, that's like saying your answer can't be an integer and real at the same time. It's like, well, actually, kind of has to be at the same time, doesn't it? Yeah, so I want the product to be odd. That's it. Does A have to be odd? Does B have to be odd? No, I just need the product to be odd. Okay? We'll see what that means in general. So let's start. Reflexive. Question. This is, I'm going to put a question mark. I'm asking the question. Is this true?
Yes.
What does this mean? This means that A times A is odd. What if A is even?
Then A times A is.
Then A times, yeah.
But is this true or not true?
It's not true.
How about we just say it's not true if A is even? I'm not gonna ask you to prove that. We've done that proof before. You go, now I gotta do a whole separate proof that the product of two even numbers is even. Okay. So it's not reflexive, is it? Oh, if A is odd, it's absolutely true. But if A is even, it's absolutely not true. Yikes. Okay. Symmetric. ATB if and only if BTA. That's what this means. That's what I have to show. I have to show that that is true. Okay. So if ATB, what does that mean? Then AB is odd. Remember, I'm starting with, no, this is true. I have to show that automatically guarantees that the other guy is true. If ATB, then AB is odd. If AB is odd, tell me about BA.
It's also odd.
It's also odd because it's commutative. Thus, BTA. Is it symmetric? Yep. Because if A is related to B, that means the product was odd. By the way, is that true for all real numbers? No, or all integers? No. It's only going to be true if they're both odd, isn't it? But if A is related to B, then B has to be related to A because the product would be odd in both directions. I'm not saying all products are odd. I'm saying anytime I have a product that's odd and I reverse the order of multiplication, it's still odd. Everybody cool with that? All right. Transitive. All right. If A is related to B and B is related to C, I want to show that A is related to C. All right, so let's start with that. If A is related to B and B is related to C, then what must be true? Then AB is odd. And what? BC is odd. Do you all agree with that? AB is odd and BC is odd. That's what that means. Now, kind of here's the question. Is AC odd? That's what I'm trying to figure out.
Not if both A is 0, AB.
But if AB is odd, then A and B both have to be odd, don't they? By the way, if one of them was even, isn't the product even? So if AB is odd, then A and B both had to be odd. If BC is odd, then B and C both had to be odd. Therefore, is AC odd?
Yes.
Yes. AC is also odd. By the way, I'm not going to have you go through and do the whole odd, there exists a T. By the way, it's not a bad idea. Right? So this is kind of crazy. We just came up with a relation that's symmetric and transitive, but not reflexive. That's actually really unusual. You'd think reflexive would be the easiest one. No, never assume anything's automatic. Now, this is a good example because it's important to see when things also fail. You could all come up with something simple that probably fails. For example, what if I said the relation is A is related to B if A divided by B is still an integer? Think about that one. So if A divided by B is an integer, then they're related. Well, is A divided by A an integer? Yep, so it's reflexive. If A divided by B is an integer, then B divided by A is always an integer, right? No, it's the reciprocal. Oh. Right? 10 divided by 2, 2 divided by 10. No, it would not be symmetric. If A divided by B is an integer and B divided by C is an integer, is A divided by C? Ooh, that would be a good one. You'd have to prove that, wouldn't you? It might be, it might not be. But there's a perfect one. It might be transitive, it's definitely reflexive, but it was not symmetric. So I have some fun just creating simple problems just as a useful tool. Now we're going to move on to the next thing. The last thing we're going to do today is another algorithm similar to the Euclidean algorithm, but it's actually a higher level one with a very specific purpose. Okay, and it's a little long. It's a little bit long. I'll tell you that right now. It's when we're doing algorithms, we don't want to take shortcuts because if I take a shortcut, I may be missing a number that I need. So, here we go. So start with a fairly simple problem. I want to start with the GCD. I'm going to do a simple one. This is pretty easy. 276, 84. Okay? Now, if a lot of you do your scratch work off to the side, which is never necessary to show the arithmetic that you're doing, but in this case it might actually be a good idea because of what we're going to do next. Now, 84 definitely goes into 276 a few times. How many times? So I need basically 276 mod 84, don't I? So what is 270? Well, 276 you just said was 84 times 3, and then what would my remainder be?
22.
20, close.
24.
24. That's my scratch work. No, none of us, that's not part of the answer, but I'm going to need this later. Do you all agree with that? So this is now what? GCD of 84 and 24. That's always the order of things. When am I done? When is there no more steps to perform? When it's number comma 0. That's when I know, because that means the 0 refers to there's no more remainder. That's when I know I've got my last term. All right, so 84 equals what? 24 times 3, and then plus 12. You're feeling pretty good about right now, I hope. Right? Now 24 equals what?
12 plus 2.
12 times 2
12 times
What?
3 plus 0.
plus 0. The plus 0 is important because that tells me, oh, okay, I've essentially reached the end. So this is GCD, and a lot of times we're not sure why we're putting the 0 because that means that I'm doing the mod. 12 times 1 plus 0, if you want to think of it that way. So the answer is 12. Awesome. That's my answer. Okay, so the top row, that's the algorithm, that's it. The second row is my actual scratch work. But it turns out the scratch work is going to become very important for the next thing we do. Because finding the GCF was cool. What if their GCD, sorry, what if the last step produced a 1?
And they're mutually prime.
Then the first numbers are mutually prime. But here's what I want to do, and this I can do for any pair of integers, whether they're mutually prime or not. We're going to exclusively use positive integers for these problems. Just because the negative, it gets messier. It's not really a point. Okay? I would like to write 12 as a linear combination of 276 and 84. And by the way, any two numbers I use, it doesn't matter what two numbers I use, I want to write my GCD as a linear combination of those two. So if my GCD ended up being 1, I still want a linear combination of my original numbers. So well, how would I do something crazy like that? Let me just give you a really simple example. If I asked you for the GCD of 7 and 5, this is easy. What is it? 1. Can you write 1 as a combination of 7 and 5? This is the kind of thing you did maybe as a little kid. Okay, let's see. There's an infinite number of ways I could do that. For example, I could say 1 equals 3 times 7 minus 4 times 5. Would that work? Could I say it's, what? -2 times 7 plus 3 times 5. Okay, I've just given you 2. How many are there? 7 times 7, or negative 7 times 7 plus 10 times 5. Do you agree there's an infinite number of ways? I can count by 7s, count by 5s, and always look for a difference of 1. What we want is the smallest, we want the smallest pair of numbers we can come up with. Clearly this can go forever. Probably the smallest pair would be 14 and 15 put together. Do you agree? Think 7 and 5. I can't do 10 and 7, but I can do 15 and 14. I can do 21 and 20. I can do this, like Captain America says, right? I can do this all day. But I'd like smaller numbers. So the algorithm, if I do it basically in reverse, I'm going to be able to come up with a simple linear combination. So that's what I want to walk you through. Oops. Where did I write it? There we go. So let me start with the 276. I'm going to start with that statement over there. So 276 equals 84 times 3 plus 24. This implies then that 24 equals 276 minus 84 times 3. What I'm going to do is a series of substitutions. Okay? Now, the next line we had is that 84 equals 24 times 3 plus 12. I now want to replace 24 with this. Because my goal, remember, what I really want to write, my answer to the question is 12 equals A times 276 plus B times 84. That's a linear combination, in other words. That's what I'd like my answer to look like. Does that make sense? The term linear combination, if you haven't had linear algebra, may not be a familiar term to you. Linear combination means you're writing scalar multiples of things. But in this case, we want integer multiples. Because if I said you could use real numbers, boy, not only is there an infinite number of answers, boy, it'd be really, really kind of sketchy if we get there. So I want happy numbers. So what I'm going to do is replace 24 with this. Oh, this is maddening. It has a black top, it just doesn't have black ink. Okay. Oh, you know what? I'm sorry. I'm getting ahead of myself. My bad. Take that line out for a moment. I'm sorry. I'm going to do a second set of things. Sorry, I got to do one more step. I got to do the 12 next. Sorry about that. I'm looking ahead on my notes. Oh, boop, boop. We have 84 equals, so now we have 24 equals. I'm taking that number, then I'm taking that number, then I'm taking that number. So now I have 24 equals 12 times 2 plus 0. Okay? Now, that's the last one. This is the answer. This was the last thing I did. That's basically the answer. We know I can now read my answer from that. Okay, so is everybody can hear? So this implies over here that 12 equals 84 minus 24 times 3. And the last one, well, the last one was done because I got the 0. Now what I want to do, okay, is I'm going to start with this one. Now I'm going to do the substituting back. So 84, where is it? Oops, I lost my place here. So I've got this. Now I'm going to replace 24, there we go, with this. There we go. Okay, let's clean that up a little bit. So what is this? That's 84. Well, how many 84s do I have technically? Times what? So I have minus 3 times another 3, that's minus 9. So it's plus 9. So how many 84s do I have?
10.
10. How many 276s do I have?
3.
I'm done. Now, I'll do a bigger problem in a moment. It takes a little bit longer, but that's it. I'm done. I've written this as a linear combination, and those are the smallest numbers I can come up with. Now, what should you be doing about right now with your calculator? Calculate that, make sure it actually equals 12. Because if it doesn't, then things went terribly wrong, didn't they? So somebody do a quick check. Does that equal 12? So to write a linear combination is not the key. So I want the smallest, I want the first one that comes up. That's the first one that comes up. So the algorithm, the algebra that you all do to do this, that most of you didn't write down because you said, I just did everything on my calculator. That's correct. Now I want to write it down because it's exactly the terms I'm going to use in reverse. So you with me on that? So let's try a bigger one. Or maybe an bigger one. Now on the exam, I do exactly this. On the exam, to make your life easier, I start with the GCF or the GCD of two numbers. You found them. Then I ask you to write the GCD as a linear combination of the original two numbers. Well, you have all the algebra already right there, so then you kind of do it, kind of in reverse. Except you cannot possibly see this in the question, can you? The GCD was 12. My original numbers were 84 and 276. You don't see the 10 or the -3. You don't see those. You actually had to figure those out. So there's no shortcut to the process. I got to do the process. Okay? So let's take a couple of big numbers. Let me. I have a calculator. Oh, I do have a calculator. Okay. All right, let's all do this. This problem is significantly longer. So, underneath on the right, 611 is 133 times what? So I really do want the div and the mod right now. By the way, if you use your fraction key, it'll actually pop up. Everybody knows that? Okay, if I use my fraction key and I just go 611 fraction 133, my calculator says 4 and 79 over 133. That means my div is 4 and my mod is 79. The simple fraction key gives me the answer. It's equal to that, and I can do a quick check if I had to. Okay, I'll do a quick check. 133 times 4 plus 79 equals 6. Okay, again, I don't want you to do this pencil and paper. I don't want you to do long division on your sheet. You have a calculator, but if you use your fraction key, there's no work whatsoever. It really isn't. So this is equal to the GCD of what? Yeah, okay. Now, 133, I can pretty much guarantee you that only goes in once, and I think my remainder is 54. I can do that one without a calculator. So now I have 79 and 54. Now, 79 equals 54 times 1 plus 25. So this is GCD of 54 and 25. Let me run out of room really quickly. 54 is 25 times 2 plus 4. This is very long. So this is now the GCD of 25 and 4. All right, 25 equals what? 4 times 6 plus 1. So this is the GCD of 4 and 1, and 4, of course, equals 4 times 1. So that's, oh my goodness. They were mutually prime. Who knew? Well, I did. All right, yuck. This is gonna take a few steps. Okay, so it's those steps here that I need now. So I have all of these steps now, okay? Just wrote them all out. Okay, one at a time. So what I want to do is start with, I'm not going to rewrite them. I'm a white pen, sorry. I just had it. Oh, here it is. Okay. Okay. These are the lines I'm going to need because I'm going to start substituting backwards. Everybody okay with that so far? Okay. So now, 1 is my GCF. And then what I want to start doing is I want to go backwards. Okay, so hold on. So I take my last one, and now I'm going to substitute the 4. Sorry. No, hold on. 25 minus 54. Oh. Sorry, I can't read my own writing. I'm replacing 4 with 54, there we go, minus 25 times 2, and then times 6. Now, here's what's good about this replacement. I know I did it right, because I'm only gonna have 25s and 54s. And then the next one, what am I gonna have? 54s and 79s. And eventually, I'll have something that has these two. Does everybody see that now as I go backwards? It's gonna be a few steps. I need better pens here. All right, so I need to clean this up. How many 25s do I have right now? Be real careful.
Uh,
13? Does everybody see that? I have 25 times 13. Minus, so positive 2 times 6. Okay. And then how many 54s do I have? 6. And by the way, it doesn't matter which side you put the coefficient on it. What does matter is you keep track of these two. I think I did it right. What should you be doing about right now? Yeah, just quickly multiply that out and it better be 1. If this is not 1, then I have an error. Everybody okay with that? Can I make a mistake distributing here, negatives and stuff? Yeah, I don't want to make a mistake, but I could. Now, the next substitution, okay, the next number involved is going to be the next higher number, so it's going to be what? 25. I'm going to replace now with what? 79 minus 54 times 1, I'm replacing 25, times 13 minus 54 times 6. Now what am I going to have? 54s and 79s. That's what I said over here. I chose one. This is the longest problem you could possibly do. Things that are mutually prime, we already know take the most number of steps. I'm doing that on purpose so you can see all of the steps along the way. It's just arithmetic though. So now, how many 79s do I have? So I have 13 79s. How many 54s do I have?
16.
careful.
That's 19.
Negative 19.
I think we have negative
Negative
19.
19.
So I have minus 54 times 19. And again, I think it's a good idea to just do a quick check. Yep, it's still correct.
So does that mean we have negative, we don't have negative 19 here?
We have negative 1 times 13 minus 6. So we have negative 19 54s.
Okay.
Is that okay? That's why, by the way, that's why I literally would check it at every step with my calculator. Remember, what did I start with? 1 equals, and this is still equal to 1. Now, what's the next one I'm going to do? I just replaced 25. Now I'm going to replace 54. And 54 is equal to 133 minus 79 times 1 times 19. And now notice I'll have a statement that has 79s and 133s. I'm almost done. Not quite done. Move this up. So this is 79 times what? And it's 133 times what? So how many 79s do I right now have?
32.
32.
Plus 19, 13, so I have 32. How many 133s do I have?
19.
Minus 19? Oops, I'll put it on the other side. Okay, and again, like always, at this point I would always be checking because the numbers are slightly too big to quickly justify in your head. It's still correct. Am I done yet? No, I have a linear combination of 79 and 133. The next step should finish it off for me. Okay, so now I'm going to replace the number 79 with 611 minus 133 times 4. All right. This is just crazy. But it's actually kind of fun. I know you guys are having fun right now. Right, George? This is what you can do when you go home. Let me just pick random numbers. No, remember, this is an algorithm. What is the purpose of this? So that I could write, you're not going to do this in this class. No, no, no. You're going to write simple computer code that does this process for you, but you have to tell it where to do every step. Do you understand what I mean? I have to tell it where I'm substituting the numbers and what I'm substituting back in. And that's where the div and mod at the beginning came from. So the point of finding the GCF was so I could write the GC or GCD as a linear combination of the original numbers. That really was the ultimate goal of the Euclidean algorithm, was to do what we're doing, which is clearly a longer, more challenging process. Getting the 1 was nice. It's the linear combination. Now, how many 611s do I have? 32. Now, it doesn't matter. A lot of times people will they'll write the coefficient in front, just because it starts reading a little bit easier. Now, how many 133s do I have?
Negative 147.
Negative 128, another negative 19, so it looks like minus 147 of them. Wow. Let's do a quick check. Try that again. I still got 1. So there's my answer. Now, is it possible we'll make a mistake? Yeah, actually, when we did this problem on the quiz last week, there were probably almost half of all the problems were incorrect. We made an error early on and we got the wrong answer, but we didn't check. The check's not that complicated, but we got a number that wasn't, in some cases, wasn't a factor of either number. So I said the greatest common divisor of these two numbers is the following, and it wasn't a factor of either one. That kind of tells me there's something went wrong there. The only check here is to do the check at the end. Now I want you to know something about these. They are mutually prime. Just an interesting observation. They probably are going to be mutually prime pretty much every time, because if they weren't, then that means maybe there's another representation. Are there more than one? Is there more than one representation of this answer? We just did it a moment ago with 12, with 5 and 7. There's infinitely many, but is there a first? Think of it that way. Yeah, this will be the first one. Could I keep going and find larger numbers? Yes, but if I did that, then I'm ignoring all the work I did. So the work I did was to figure out how to do this in reverse. Yes, it's messy. This is the longest problem you could possibly run into, the mutually prime problem, because there's so many more steps. The first problem I did, there was, what, 3 steps or something? That's probably much more common, okay? Excuse me. So we have now finished all the material that's going to be on the test. That we've finished chapter 8. Starting tomorrow, the course is going to take a very, very different turn. Starting tomorrow, the course is going to be heavily calculator based, in that you're going to be doing calculations. Not that it's hard, but we're going to be doing a lot of things with factorials and stuff like that, where you got to calculate really big numbers. I really need you to have a calculator that you are very, very familiar with. This is where a graphing calculator becomes the least likely candidate. If you have to go to a menu to do a calculation, that means you're going to be using menus for every calculation we do from here on out, and that just takes forever. I like the cheap $9 departmental calculators that are 15 years old, where every single function is a main key. So everything you can do on your graphing calculator, I can do in 1/10 of the time. Literally. The only advantage of the graphing calculator is it might be able to do larger factorials, which just aren't going to come up. I don't say this jokingly. I have a TI-89 titanium. I really don't use it anymore because I used it primarily for, well, graphing. That's what graphing calculators are for. They're not for calculating, they're for graphing. Cheap scientific calculators are for calculating. Now I don't do any of my graphing on my calculator, I just do it on Desmos. So if I've got to do a calculation, I want it to be quick and fast, and I want it to be a main key. I don't want to have to go through menus. A lot of you don't mind going through menus, it just takes longer, and I'm going to get the error message way too often because I didn't complete something. Have a calculator you are comfortable with, because the next literally 2 weeks is going to be all stuff where we're calculating. It's not going to be hard stuff, but it's going to be stuff that you're not going to be able to do in your head on a regular basis. We're going to do some elements of probability. The topic is called combinatorics, which is something that I studied heavily in college and grad school. That's what I did more of than anything else. That's the area where I would consider myself much more expertise than a lot of the other stuff. But I also know that you can't do math in your head when the numbers are big if you're doing calculations. So you want to have this out of the way. If you're a computer scientist, you're very likely going to take an upper division course in combinatorics. So what we're doing is getting a glimpse. If you've had Math 119, you actually got a glimpse of combinatorics when you did the permutations and the combinations and stuff like that. That's where it comes from. But we're going to do much bigger stuff. There's a lot of really cool problems out there. We're not going to be able to do all of them because some of them are too high level. But there are really a lot of great problems, and the way we do the calculation sometimes can be very, very simple. There's several formulas involved. So that's what we're doing next, and that will mostly constitute the third exam, because if you look at the outline, we're going to spend quite a bit of time. Let's see, sorry. So starting tomorrow and Wednesday, then we have the exam Thursday, then we have the weekend, then we have Monday, then we have a holiday, then we have the Wednesday, and we have the Thursday, and that finishes it. So the entire exam 3 is going to be chapter 9. Okay, we do a little bit at the end that's completely different from that. So again, it's not a warning, I just want to make sure you guys are properly prepared. You don't want to be the one person sitting there waiting for everyone else to do the calculation. Because then when you have to do it on your own, you're not going to be as comfortable. So I really want everybody to have a calculator in class from this point on, because we're going to be needing them. Just because, you know, it might be something as simple as, all right, our answer is 6 factorial. Let's give a numerical value for that, and, you know, I'll do it by hand. All right, can I go ahead and stop that? So press the red.